In the last section, we reasoned through how you can use the singular value decomposition to solve the linear least squares problem. And that's all very nice, but we still don't have a computational method for computing the singular value decomposition, and therefore it's not a practical method yet. Well, we also had the method of normal equations, but we cautioned you that that might square the condition number. So let's look at yet another approach that's based on the QR factorization, and notice that we have practical methods for computing the QR factorization. We can either use Gram-Schmidt or modified Gram-Schmidt to compute Q and R, or we can use householder QR factorization. But let's just assume that through some means we've computed Q and R, where Q is an n by n matrix with mutually orthonormal columns. A is m by n and has linearly independent columns. And if that's the case, then we know that matrix R, upper triangular matrix R, is non-singular. It has no zeros on the diagonal. All right, so we want to solve this problem right here. Okay, well, what do we know? We know that A times x hat is equal to B hat, where B hat is the projection of B onto the column space of A. So, we could replace B by A times A Hermitian A inverse times A Hermitian times B. But we also know that the column space of A is the same as the column space of Q. So we could instead project onto the column space of Q. Okay, and that's a simpler formula. That's Q Hermitian times B. Sorry, it's Q times Q Hermitian times B. Why? Because the Q Hermitian Q that ends up in the middle here, that you end up inverting, is just the identity matrix. Now, we can then also replace A by Q times R, and what we find is that Q times R times x hat is equal to Q times Q Hermitian times B. Okay? And then you can either say, well, I know that you need to take the same linear combinations of Q on both sides, and therefore this vector must be equal to that vector, or you can multiply both sides by Q Hermitian transpose. Regardless, the x hat that solves this problem is R times x hat is equal to Q Hermitian transpose times B. And remember that we said that R is non-singular, it has no zeros on the diagonal because A has linearly independent columns. And bingo, we've got ourselves a way of solving the linear least squares problem using the QR factorization. Now I just want to stress, what you want to do is update the right hand side by multiplying it by Q Hermitian transpose. That's just a matrix vector multiply. And then instead of computing the inverse of the triangular matrix, which is very costly, what you end up doing is solve with the triangular matrix. And notice that solving with a triangular linear system is relatively straightforward and cheap.